Hey there, Calculates. Mr. Super here, of course, and we're going to try something different today. As I promised you, said I'd be sending some information along, so we're going to try doing a lesson today on slope fields, and I think this is something that's doable, and I hope this video is useful to you. Good luck. So I'm Super, and I've got my dog, so together we make Soup Dog. This is the sheet that you should be looking at entitled 6-1 Slope Fields Day 1. Our warm-up is going to involve finding slope of lines that go through 2 points. Again, we've been doing this for quite a while. I'm going to give you a second here to answer our warm-up questions A, B, and C. Do pause the video and figure those values out. So for A, going from -3,5 to -3,9, our change in y over change in x, we get 4 over 0, which again is undefined. That would indicate a vertical line or a vertical tangent. For B, going from -3,5 to 6,5, our slope is 0, which would indicate a horizontal tangent line. And of course we all know that a derivative is the instantaneous rate of change. It's a slope machine. It tells us the slope of a tangent line, and who could forget that a derivative is also a limit. So we're taking a look at a derivative. We have dy dx is equal to 3x squared, and we're going to find out the function that has a stated derivative. We've done this before, where we go backwards to find the function that has a stated derivative. What we notice is the derivative is defined explicitly in terms of x. So this is pretty easy to do. We're going to find the antiderivative. We know that the function try that again. We know that the function y, or f of x, is going to have a degree that is 1 larger. So it would go up to a 3. And again, I'm going to double check. 3 times the coefficient of 1 does give me 3x squared. So this would be the general function that would have the stated derivative of 3x squared. And we also know that there would be many different families of functions that would have this derivative. So we're going to put an emphasis and say that there could be some constant c. And again, we want to really put some effort into that this is the general function that would have the stated derivative, where c could be any constant. And when we take this derivative, we do in fact get dy dx is equal to 3x squared. So again, what can be said of this solution? It represents a family of functions with the stated derivative. Now, as we've done before, that if they give me a clue, if they tell me something that's true about the function, they give me an x and a y value for the function, I can substitute those in, and then I can solve for c. So that's what we call solving a differentiable equation. But today's lesson is going to be on how we can use a derivative to generate a bunch of tangent lines for different locations where I don't really know anything about the function other than that there's a whole family of functions that have the stated derivative. Okay, so you're probably asking, what is a slope field? So a field is looking at different locations on the coordinate grid and looking at the instantaneous rate of change based on what the derivative function is. So there's 3 bullets that I'd like you to fill in here on your notes. Alright, the first one is a slope field is a plot of the instantaneous rate of change at a location. And I like to affectionately call those mini t's. They're mini tangent lines. Slopefield shows the family of curves with the stated derivative. So we're going to be taking a look at that. And of course, because we're dealing with a tangent line, it's showing local linearity at a point. So what we have here is a coordinate plane. And again, going back to our derivative, 3x squared, and we did find the family of functions that has a stated derivative. So what we're going to do is we're going to be taking a look at all these locations. Anywhere where you see a location of a point, we're going to be figuring out what the instantaneous rate of change is. So again, my derivative is based strictly on the value of x. So I'm going to be taking a look at where x is equal to 0. So that would be at, of course, origin, at this point, 1, 0, or I'm sorry, 0, 1, 0, 2, 0, 3, 0, 4, as well as below the origin. Those are all locations where x is equal to 0. If I substitute that into my derivative, I get 3 times 0 squared, of course, gives me 0. So I'm going to put here when x is equal to 0, the slope of the tangent line is going to equal 0. Well, what does a tangent line look like if it has a slope of 0? Of course, it's a horizontal tangent line. So what I'm going to do at these locations right here, I am simply going to put in a mini tangent line, stating that if this were a point that was on this function, it would be going through that point horizontally. If it was going through this point, it'd be going through it horizontally. So I'm going to just draw in a bunch of mini t's to represent the instantaneous rate of change at that point. Again, no information was given to me about a point on this curve, so we're just going to entertain the idea of what would the slope look like if that point was a solution to this function. So let's take a look at when x is equal to 1. Let's look at the slope of the tangent line. So again, if I substitute in 1, square it, multiply by 3, I get a slope of 3. Well, what would that look like? Well, it would be a rise of 3 and a run of 1. So this would be a line with a slope of 3. So what I'm going to do is kind of visualize this slope right here, and obviously this is where x. So I think that the slope would look something like this, a slope of 3. And I'm going to copy that on down here because these are all the spots where the x coordinate is 1. And again, I'm just approximating the slope, and I think that's what a slope of 3 looks like. Let's go ahead and look at when x is 2. I'm going to figure out the slope of the tangent line again by again going to the derivative. Derivative is the slope machine. I'll square the 2. I get 4 times 3 is 12. Well, how would that change the slope? So again, I would have to rise 12 and go over 1. That is quite a bit steeper than a slope of 3. Now again, I'm just going to really kind of tighten this up. These are all the spots where x is equal to 2. And if I go to 3, as you can quickly guess, it's going to continue to get steeper and steeper. So I'm going to just kind of give, it's almost going to appear vertical the farther I go to the right. Now again, this is just an approximation. So I'm going to go over to the other side of the y-axis, and I'm going to be looking at these x values because again my derivative is contingent on what the x coordinate is. So I'm going to go ahead and look at when x is equal to -1, when x is equal to -2, when x is equal to -3. So here I'm going to get 3 once again. I'm going to go ahead and plug in the tangent line, -2. I get 12 once again. And 3, squaring the -3, I get 27. All right. So I'm going to come over here to where x is equal to -1. And again, that would be this set of points right here. And my slope is 3. Now again, notice that when x is 1, I had a slope of 3. So I'm just going to kind of mirror that slope, that rate of change. And again, when the slope was, or when x is -2, my slope was 12. So it's getting more vertical. Giving it just a slight slope. Should be steeper than what it was here. And then again, I'm almost getting vertical as I go out here. So this is what we call a slope field. It's looking at locations on the coordinate grid and what is the instantaneous rate of change there. And all of these are miniature tangent lines. So if we look at this, what we're doing is we're showing this family of curves that should look like cubic functions, just being vertically shifted up and down. So one thing that they might ask you to do is say, hey, if there was a solution at 0, 0, I've got a point through here, what would the function look like that would contain that point? Well, obviously we know it would be x cubed, because x cubed contains that point. So what we do is, if I do have a slope field, I'm going to try to kind of go with the flow using the tangent line. So as I go through this point, it's horizontal. As it goes this way, it's going to have to kind of go through, and it's going to continue to decrease, decrease. I'm kind of following the slope fields, and as I go up and to the right, it is increasing. So right here I can use a slope field to kind of get the trend of the points using the direction of the slope field to guide the curve. Again, if I were up here at another point, let's say they told me it went through this point right here. So again, the tangent line's telling me it's behaving very flat here. I've got a horizontal tangent line, so the function is going to kind of level out here. So again, as I go to the left, it's beginning to decrease, and I'm just following the field. So I'm going to come across here, I'm going to go up like so. So this would be the function with the stated derivative that would contain this point. And I could do this infinitely many times based on where they give me the point. So again, here's a slope field that we had generated from a derivative. We did find the function that has this derivative. Not going to be necessary with everything that we do today, but we were able to easily find the function, and we could see the family of curves, x cubed plus c, that are being generated on top of the slope field. Now taking a look at example 1.